Well, welcome back to Human Anatomy videos. Now, this is a really interesting video because human anatomy, even though we're talking about all of the bones, all the muscles, everything involved with the human body, we have to understand chemistry. And so, this particular chapter, and in your book it devotes a full chapter to it, but we're going to give you an overview. We're going to give you an overview of chemistry. So chemistry is kind of my area. I teach a lot of chemistry classes. That's what my degree is in, and that's my area of expertise. And I love the human anatomy, and I love the way chemistry ties into that. So I'm going to give you an overview of chemistry here. Now, once again, anything that's in this video could definitely be on the test. You're beginning to learn some of the little things we talk about, even though it's not like we're trying to find something little to quiz you on. It's important stuff. So let's look at this. Okay. So what is chemistry, and why is chemistry so important? Well, I've got a small periodic table here. We've downloaded one up on yours, and we have the periodic table list of all the known elements, okay, and that's good. But chemistry really is about one thing, okay? Chemistry is about being stable. And stable means having a zero charge. Now, what do we mean by a zero charge? This is when is something stable and when is something unstable, and when does your body need a charge and when does your body not need a charge, and when does a charge hurt your body, and when does a charge cause your body to react differently, and when do we have neurons, synapses, and that type of thing. So the whole key here, once again, so get your frame of mind, think like a chemist. It's like a thing stable. They have a zero charge. Now, we talked about the different subatomic particles, okay? So we have electrons, protons, and neutrons. Now, a lot of you have had a lot of this, a lot of you have had this, and you're doing good, but let's refresh, let's make sure we know where we're at. Electrons have a negative charge, protons have a positive charge, and neutrons have no charge. So, are you more of a, let me grab another marker here as we go. Are you more of a proton person or more of an electron person? Are you more of a positive person or are you more of a negative person? All right, so electrons negative, protons positive, neutrons no charge. So how does this come about? Well, it's kind of interesting because, and once again, a lot of you have had this, inside of the nucleus, okay? Inside of the nucleus, we have the protons, we have the neutrons, we have a plus charge, and we have a neutral charge. Well, that's kind of cool, okay? That's kind of cool. But orbiting this is a little electron, okay? And that electron has a negative charge. Now, when we look at the periodic table, okay? When we look at the periodic table, for example, every single element, let's do carbon here. Okay, let's take a look at carbon. Has the symbol, okay? The chemical symbol, they all start with a capital letter because that's how we know we have a new symbol. So that one's carbon, Ca, that's calcium. All right, so then we have a situation where every time we have a capital letter, we have a new element. So let's also look at carbon. There's a number at the top, okay? All right, and then there's a number at the bottom. Now, these aren't the same for every periodic table. 12.001. Now, we have in that deal, there's all kinds of periodic tables out there, and a lot of times people have all kinds of stuff on their periodic table. Chemists just like this. These are the only three things we want to know. This periodic table is actually the one that's approved by the American Chemical Society. That's all I want to know. I don't want to know the melting point, the boiling point. I don't want to know all that stuff. If I want to know that, I'll Google it. I'll look in the chart. But these are the only things I need to know about the element. First of all, we have the atomic number. The atomic number is a whole number. That's how we put everything in order. Hydrogen is number 1, helium is 2, lithium is 3, beryllium is 4, and we go so forth. So we go in line. The atomic numbers, for example, carbon, the atomic number equals 6. Now, the atomic number is the number of protons and the number of electrons. Okay? So, if I ask you, you should know the number of protons and electrons for everything in the periodic table. Now, once again, you have a periodic table to download and copy. It's one of the links that you have on your Moodle. Okay. So if I ask you, so that means it's exact things. So what does that mean? So carbon has how many electrons? Well, it has 6. How many protons does carbon have? It has 6. It's not a combination, it's both of them, okay? So let's look at the charge of carbon, okay? So everything on the periodic table is how it's found in its natural state. Everything has a 0 charge. So carbon, okay, so carbon has a number of protons. It has 6 of those, so that's a plus 6. It has 6 electrons, so that's a minus 6, so it has a 0 charge. Wow, that carbon is stable, that carbon is good, okay? So that's the atomic number. So how do we figure the number of neutrons, okay? Well, that's the other thing we have. The other number that we have is called the atomic mass number. The atomic mass number basically says, what does 1 mole of that weigh? Okay? So for carbon here, we see that the number 6 is the atomic number, the number of protons, the number of electrons. But then we got the mass number, 12.001. Okay? So the atomic mass number for carbon is equal to 12.001. So that's the mass number. Okay? Now, the number of neutrons, okay? The number of neutrons equals, okay, equals the mass number minus the atomic number. Now, what we do is we round that off. So for carbon, okay, so for carbon, the mass number is 12.001. We don't round it up unless it has a 5 there or higher. So the mass number is 12. What's the atomic number? The atomic number was 6. Okay, so it has 6 neutrons. Okay, all right. So let's draw a quick carbon molecule. As I do that, let me tell you, and we'll be sure to put down in our notes here, that the 3 most common elements in human anatomy, in the human body, the 3 most common elements are carbon, hydrogen, and oxygen. So carbon, hydrogen, and oxygen. 90% of all of the human body is made up of carbon, hydrogen, and oxygen. Okay? So let's go back to the old 2-dimensional model, and let's do the old high school model, and let's draw this. Let's say here's the nucleus, so we're going to draw carbon. Okay? So carbon once again had 6 protons. We determined that it had 6 neutrons because we had the mass number of 12 minus the atomic number of 6 equals 6 neutrons. It's not always the same, it just happens to be there. And then we draw a little 1-dimensional figure here, and we say, okay, 1, 2, 3, 4, 5, 6 electrons rotating around. Now, here's what I want you to understand. I want you to understand that when we do the mass number, okay, it's mainly protons and neutrons, because I want you to understand that the most important element that we deal with, the protons and the neutrons, we talk about atomic bombs, those are pretty important, okay? Those are critical, but what we're talking about in the human body, the neutrons stay together, okay? The neutrons are right here, and it's like they've got this big circle of something going around. Well, the circle going around holds it all together, okay? It's kind of like I had a dog one time that was a cow dog. And he took all the neighbor's cows and he put it right there, and he kept going in a circle, and he wouldn't let those cows out. That's what the electrons do. They keep the nucleus in there. It's kind of like that whole Pandora's box. You don't want to let it go, or crazy things will come out. So the nucleus here has got to stay intact, or we have a nuclear bomb. That's why hydrogen is so interesting, because hydrogen has 1 proton, 1 neutron, but only 1 electron. Wow. When we take that electron out of hydrogen, okay, then look, we make this really vulnerable for the nucleus. Okay, and then if this nucleus develops and the neutrons get out, then we have a nuclear bomb. Okay, so what we're interested in here primarily is the electrons. Now, if you were to let's put this in perspective, okay? Let's see how big an electron is compared to protons and neutrons. Now, this is just an example here. If protons were the size of a basketball, okay? If protons were the size of a basketball, neutrons would also be the size of a basketball. They're about the same size, but the electrons would be the size of a ball on a ballpoint pen. So you get your pen out, see if it has a little ball on the tip. That's how big the electron can be. As a matter of fact, when we weigh this whole molecule, the electrons are so small, they don't weigh anything. They don't weigh anything. When I weigh these, I get the whole weight of the molecule. The electrons don't weigh hardly anything at all. It would be like if I took your desk or your chair or your stool and put it over here, and then I weighed it, and then I put a little grain of sand on there, and I went over and I re-weighed it. I would be like, whoa! But I know it weighs more. There's a grain of sand on there that wasn't on there before, but it's so insignificant that it doesn't weigh. Now, that's where the electrons are. They seem totally insignificant, but here's the problem. The electrons are traveling at the speed of light, 186,000 feet per second. 186,000 feet per second. So these electrons are traveling so fast. So that's why we thought that the molecules look like this. There was a little dot for the nucleus, and then we could just see this. So our early diagrams look like that. Because the electrons are traveling so fast that we couldn't see the individual electrons. So these electrons that are traveling so fast, that's what dictates what happens in the human body or the electrons. Okay, so now let's go one step further. All right. Now once again, this is a real overview of the whole chemistry course. Now let's talk about where we go from. Okay, now we'll stay with carbon here for a little bit. This is a one-dimensional molecule. Now, assuming that the world was one-dimensional, which it's not. One-dimensional means we draw everybody on a cartoon page. We draw everybody on a piece of paper. And we just keep drawing a whole bunch of figures, and we keep moving them, and they move. That would be one-dimensional. No, life's more than three-dimensional. Four-dimensional, five-dimensional, six. Let me show you what I mean. Okay. So this is a nice high school model. It tells us what we're doing here. In high school, we try to draw these different levels of electrons, and we show that we have different subgroups and different things. Okay. All right. Let's go one step further. Let's show you the college model. Let's show you what happens. By the way, if you need to take freshman chemistry, we offer that. I teach that. I love that class. You really learn a lot from that. If you need a science, chemistry fits everything. Chemistry is a good one to take. All right, so here we go. So we have the nucleus. Okay, right? Yeah, that's good. The protons and the neutrons. But we have electrons in different energy levels. Okay, the energy levels. Okay, so let's do this. Let's go energy levels for electrons. Now, once I do this, it'll make a whole lot more sense. Okay, there's an S, a P, a D, and an F. Now, I like to say the word speed fighter, because when you say speed fighter, you hear speed fighter, S, P, D, and F. Those are the different levels, the different types of electrons that we can have. Okay, S, P, D, and F. Now let me move this over a little bit. Now let me show you what I mean. Now, in the old diagram, here's what they used to do. They used to put protons and neutrons. When I say old, I just mean high school. We've been doing the actual model for years. Okay, so what they would do in high school is they'd say, okay, here's the S, here's the P, here's the D, and here's the F electrons. Once again, really nice if life is one-dimensional. But this is where we get confused. You know, I've had other teachers come to me and go, you know, man, this model makes no sense. I'm confused. So if they're confused, you know, you can imagine. Let me show you why. This is the way it exists. Now, once again, we're going to show you on a one-dimensional board here. But here's your neutrons and your protons. All right, now the S electrons travel right around the nucleus. They just travel right around the nucleus. That's all they can do. They just travel right around the nucleus. They can have up to 2 electrons, okay? They can have up to 2 electrons that travel right around the nucleus. Oh, cool. So those are in there close. Those are in there close. That's all they can do. They can't go any further out, okay? Now, let's talk about the P's. The P's can have up to 6 electrons, okay? But what do? They are able to travel out away from the nucleus. They take off, boom, and gravity brings them back. They take off and gravity brings them back. They take off and gravity brings them back. But not only right there, they also come out of the board, boom, okay? Here's my nucleus. Here goes the P electrons, boom, and they come back. Here and they come back. Over here and they come back. Over here and they come back. Over there and they come back. Wow. I'm fixing to show you how do we know how many p electrons there are and how many s? Okay, but we've got another deal. Okay, the d